Hello everyone, my name is Yang Cai. My final project is SymPy-based simulation of a 5-stage pipeline processor. In this project, I use Python and SymPy to simulate processor execution and compare three different processor models. A simple non-pipeline microprocessor, I may call this simple. A 5-stage pipeline processor without forwarding, I may call this no forwarding or without forwarding in this presentation. And a 5-stage pipeline processor with forwarding, I may call this forwarding. The main goal of this project is to understand how pipeline improves performance, how data hazard affect pipeline, and how forwarding paths can reduce loss and improve CPI and IPC. Next, let me talk about some background of those three models. So this is the simple microprocessor model, and this is the base model. So here in this model, each instruction goes through all 5 hardwares: instruction memory, register, ALU, data memory, and register. Okay. However, the next instruction cannot start until the current instruction finish all 5 stages. The advantage of this model is that it is simple, it's easy to design, and there are no pipeline hazard because instructions do not overlap. The disadvantage is that performance is low. Since every instruction takes 5 cycles, the CPI is always 5. Also, the hardware is not fully utilized during the whole execution time. The model is useful as a baseline because it shows how much improved pipeline can provide. Next is the 5-stage pipeline microprocessor. So here, there are 5 stages of this model. First one is IF, second one ID, EX, MEM, WB. So the between each hardware, it inserted 4 different registers to split those hardwares, which can split the full process into 5 stages. The main advantage of pipeline is that multiple instructions can be processed at the same time. For example, where one instruction is in the execute stage, another one can be in the decode stage, and maybe another one can be in the fetch stage. The overlap improves throughput. Ideally, after the pipeline is filled, one instruction can complete every clock cycle. However, the pipeline is more complex than the simple processor because instruction overlap hazard can occur. The main hazard type are structure hazard, state hazard, and control hazard. In this project, I focus mainly on REW raw data hazard because they directly affect the forwarding and the store logic in the simulation. Next one is a 5-stage pipeline microprocessor with forwarding. So here, 3 hardware forwarding paths are generated or created of this microprocessor. So its path A is from MEMWB register to EX stage, path B, EX MEM register to EX stage, and path C is MEMWB to MEM stage. And the goal for forwarding is keep the pipeline moving as much as possible. And here also it can fix the raw hazards. Next is the simulation methodology. For the simulation, I use Python and SymPy. The simulator has several parts, so those are some, I will introduce some main parts of that. So first, the instruction parse with each instruction, and the instruction parser with each instruction and identify its operation rate, destination register, EX stage, source register, MEM stage source register, and whether the instruction writes a register or not. Second, the hazard detection function check whether the current instruction depends on previous instruction, and third, the scheduler inserts knobs when the stores are needed, and fourth, the SymPy simulation runs the schedule, the instruction sequence, and generates a cycle-by-cycle pipeline table. Finally, I calculate performance metrics such as total cycles, CPI, and store counts. So here, let's say this is a instruction parser. So it's used to pass the program. The instruction parser is important because it converts instruction strings into structured information. For ALU instructions such as add R1, R2, R3, R1 is a destination register, R2 and R3 are EX stage source registers. So the EX stage source register or MEM stage register. So those two information are also very important because it determines whether it's pass C, pass A, or pass B for the forwarding model. So this is the parse result of that. So as here we can see, so this is a demo instruction, demo program which has 6 instructions, and after we pass it, we know its operation is the type of the hardware, destination, source, those stuff of that. Next function is the store handling without forwarding. So the function to deal with that. So for the pipeline without forwarding, the simulator inserts stores when a raw dependency is found. Without forwarding, the current instruction must wait until the producer instruction writes the value back to the register file. The function has previous 2 scheduled instructions. If the current instruction depends on immediately previous instruction, it inserts 2 stores. If the current instruction depends on the instruction 2 position earlier, it inserts 1 store. So older instructions are assumed to have already reached write back or be available through normal register timing. Next is the store handling with forwarding. So this function would deal with the forwarding model. So the simulator will use pass A, pass B, and pass C to reduce stores. The EX stage source, for EX stage sources, the simulator checks whether the needed register was produced by a recent instruction. If the producer is the immediately previous ALU instruction, then pass B is used and no store is inserted. If the producer is older, pass A is used or normal register available is assumed and no store is inserted also. If the producer is the immediately previous load instruction and this is a load user hazard, in this case, 1 store is inserted and then pass A can be forwarded the loaded data. For MEM stage source, meaning store data for SW store word, pass C is used here. If a previous instruction produced the store data, it can be forwarded to data memory, so no store is needed. The forwarding logic greatly reduced the number of knobs comparing with no forwarding pipeline. So this part of the code is for path A and path B, and this is for path C. And next part is the SymPy-based runtime pipeline simulation. So here, each instruction is modeled as a SymPy process. The instruction enters the pipeline at its start cycle and then moves through the IFID, EX, MEM, and WB stages. Each stage takes 1 clock cycle. The function instruction process models how 1 instruction moves through the 5 pipeline stages. During each cycle, the function recalls which instruction is in which stage. The function runs simple pipeline simulation, creates a SymPy environment, and starts 1 process for each scheduled instruction. The scheduled instruction list already includes knobs, so there is a function to insert knobs. If stores are needed, then it will insert knobs for the final table. the final list or the scheduler. So when the simulation runs, knobs are moved through the pipeline and present store cycles. Finally, the pipeline log is converted into a pandas data frame. This gives a cycle-by-cycle pipeline table, and we use the table to show how instructions overlap in pipeline. So next part is I use a demo program to show what one run of this simulation. So for the demo simulation, the purpose is to show how independence creates stores and how forwarding reduces those stores. So here, this is the demo program. So those are the instructions. Here, this is a result which after the simulation of no forwarding model, you can see that the knobs are inserted here, and since this is for add, it yields R2, and R2 is a destination of I1, so here this is raw hazard here, and for instruction 2 and instruction 1 is the same R1, R4, R4, R6, R6, R8, R8, so the knobs are inserted here. This page shows the demo model, the demo program, the result with forwarding. So here we can see we have way less knobs here, only one, and the data, for example, this one from I0 to I1, I0 and I1. So pass B is used to forward the data. I1 and I2 still pass B, and everything shows here. So from the result of the demo simulation, we can see that the total cycles reduced from 30 to a 5-stage pipeline, even no forwarding to of 20. So the improvement is very huge. And after we add forwarding, the hardware of the forwarding path, the total cycles even dropped to 11. So this is a very huge improvement of that, and forwarding is really very useful here. So after run for only one program, one fixed instruction, fixed program, then the next one, then we may think about to generate some random program and then run maybe 1,100 program to see what's the difference of that. And here, this is a random generator function. So the random generator function creates random instructions from A, add, sub, multiple, LW, and SW. The important part is that the generator does not always create completely independent instructions. So here, there is a function to generate the probability of 45%, 0.45, to let the previous source like the previous destination register becomes the source register. So here, for ALU instructions, the dependency register can be one of the ALU operands, and for LW, the dependence register can be the base register. For SW, the dependency can be either the store data register or the base address register. And here, I choose 0.45 to create the raw dependencies, because if the probability is too low, there may be no enough data header to show the effect of forwarding. And if it is too high, then it shows that every instruction it depends on a previous result, which is not true for real thing, for the real program. So this is code to run 100 programs with 10 instructions each. the result shows that the simple processor stays as CPI 5, and the non-forwarding pipeline has much lower CPI because of pipelining, and the forwarding pipeline has lower CPI because it removes those raw stores. For 10 instruction program, even the ideal no store 5-stage pipeline needs 10 plus 4 cycles, which is 14 cycles. So the ideal CPI is 1.4, and we can see doing the simulation, it's very close to 1.4. And here, for the CPI of each models, if we can comparing the no forwarding with simple, the CPI drops 60%. If we comparing forwarding with simple, drops 70.9 to 93% of that. And even we comparing the forwarding with no forwarding, the CPI drops 26%. And here, if we look at the average CPI, we see it dropped like 0.5 of the average CPI. But if we see the variation of that, the orange one, this is no forwarding, the green one is forwarding, we see the variance of the forwarding variance is way less than the variance of no forwarding. So this is some conclusions of that. So next, we may curious about by different number of random programs, what may be the result of that. So in this experiment, I tested different numbers of random programs, 10, 50, 100, 500, and 1000. Each program still has 10 instructions, and the dependence probability is still 0.45. The purpose of this experiment is not to show that all performance improves when the number of programs increase, the processor architecture does not change. Instead, the purpose is to show how results stability. Since all groups use the same program links and the same dependency probability, the average CPI and average store counts should be similar. The difference is the 10 program is similar, is a smaller sample, so the average may be affected more by random variation. With 1000 parameters, the result is more stable and reliable. And those are the dot plot and histogram of that. Next is the experiment 2 is a program links trend. So in this experiment, I fixed the number of random programs at 1000 and changed the number of instructions in each program. The tested program links are 3, 5, 10, 20, and 50 instructions. The purpose is to see how program links affect CPI, store counts, and stability. The simple process always has 5. For the pipeline model, CPI decrease as program links increase. This happens because a 5-stage pipeline has field and join overhead. For short programs, this overhead is large compared with the total number of instructions. For longer programs, the overhead is spread across more instructions. For example, with 3 instructions, the ideal no store pipeline cycle counts 3 plus 4, so which is 7, then CPI is 7 over 3, which is 2.33. However, for 50 instructions, so the ideal no store cycle counts is 50 plus 4. So it's 54. 54 divided by 50 is 1.08. So even though nothing changed, but just increased the instructions, we can see that the CPI dropped significantly. So here, the result shows the result of the experiment 2 shows that the forwarding pipeline consistently has the lowest CPI and for 50 instruction programs, the no forwarding pipeline has about 24.6 stores on average, while the forwarding pipeline only has 2.2 stores. So I don't have time to cover so much things of that. And here, this one can show that, okay, the with forwarding distribution is significantly less than the no forwarding distribution. And the last one is the important result of those different instructions. We can say that the CPI is reduced simple with no forwarding, 41 for 3 and 64 for 50 instructions. And the CPI for the simple with forwarding is 52 and 50 is 77. And the last one, no forwarding with forwarding, we say as the instructions number increase, the CPI reduction also increase. So sorry I talk about this so fast. There may be something I didn't tell about that clearly enough, but thank you to join my presentation.